Okay, happy Tuesday. Thank you for being here. I've got some announcements for you today. Let me pull up the document. Um, One of them is the Mission and Ministry Center is doing a retreat that's happening this weekend if you want to go. It's all about the theme is finding your north, which is um, clarifying your vocation of what you're meant to do in life. Um, it's this weekend. Cost is $45, but there's financial assistance. So I just thought I would put that out there. So there's that. There's also a book scholarship that I want to let you know of. This is a book scholarship that I received when I was a student here. Um, and so I think it's once every year. So if you didn't get it in fall, you could get it in spring. If you got it in fall, you can get it in spring. Um, so it gives you up to $250 to buy your textbooks. Um, yeah, and it's put on through the Intercultural Center. So if you Google Intercultural Center book scholarship, you'll get there, or I can forward you along the email. Okay, so retreat and um, book scholarship, those are my announcements. I will also say I went on these kinds of retreats when I was a student, and they were really great. I really enjoyed them. So those are both things that are going on. So I've got most of your Eulerian packets. If I didn't, please make sure I get them by the end of class. And homework 3 is due tonight. So either you can give me your hard copy or you can turn it in on Canvas. If you give me your hard copy, just make sure to snap a picture of it before, just in case something happens. Yeah. Homework 4, we're going to talk about digraphs today. That's assigned. So you'll see it's basically the same thing, just with arrows as chapter 2. And so we have like a lot of the same problems. And so my idea is I've given you the packets and I'm gonna split us after we go over like the basic definitions. I'm gonna split us into random teams and we're gonna have a race and like you'll put your answers up on the whiteboard and the team who gets through the most problems and by the end of class wins either chocolates if you want or eternal glory if you don't want chocolate. So that's the plan for today. And then at the end of the chapter, there's some case studies which we'll look at after we get through all of the problems. Okay, let's pull up the document. Okay, so this chapter is all about directed graphs. And we shorten directed graphs to digraphs. They mean the same thing. It's just one is slightly shorter to say than the other. And directed graphs or digraphs means there's some sort of direction going from one thing to another. So if we can define it, our definition is we've still got a graph, G equals V comma E. So same as before. But the only addition here is now that edges have a direction. So we're still working with a graph, but there's just some additional information on edges. So whereas before, let me see, can I zoom this out a little bit? Okay. I think I like it zoomed in a little bit better. So whereas before we had something like if we have a vertex U and V and an edge between them, this is what we were working with before, where there's no direction there. This is also implicitly, like if we were taking a walk on this graph, we could go from U to V. We could also go from V back to U, right? So those directions are implicit. And this is what we call bidirectional, right? Bi meaning two, so you can go one way or you could go the other way. So we're gonna just kind of speed through all of the definitions because a lot of the same things that we learned about graphs apply. It's just now there's arrows added. So some things are a little bit different, other things are mostly the same. So in terms of simple graphs, the same sort of things apply. I will note that, let's say we've got two vertices here, and here we would say this is a multiple edge, right? Because there's two edges going between two vertices. If we add directions on them, this is still a multiple edge. And the reason why is we've got something, if we label them A and B, there's an edge going from A to B and another edge going from A to B. So since there's more than one of them, then that's a multiple edge. For a loop, remember that's what a loop looks like just in a non-directed graph. We had an arrow on it, it's still a loop. That would still not be simple. Let's look at another one. Okay, so let's say we've got one arrow going one way and one arrow going the other. This is a simple graph because there's not more than one edge going to a vertex from, so like if we label these A and B again, there's not more than one way to go from A directly to B. There's not more than one way for B to go directly to A. We can go from A to B and from B back to A. That's a simple graph in directed land. So the thing with the multiple edges is they're multiple edges if there's more than one going in the same direction. Any questions on that one? Yeah.
So you said, I'm sorry, I didn't hear you when you were talking about the loop. Did you say that it is simple or is it not simple?
Not simple. Other questions? Yeah.
The multiple edge one and the simple graph, they're the same thing. The only difference is like the direction.
Yes. Yeah, and so the multiple edge is defined by we've got more than one edge going in the same direction. For this one that's simple, they're going in different directions. Other questions? Okay. So again, we're gonna not look at the packet problems yet. We're gonna just go through all of the definitions and then I'll release you to work on those. Okay, so in terms of the word adjacent, that's the same as before. So let's So for adjacent, for like A and B, they're adjacent because they're joined by an edge regardless of direction. Even if there wasn't an edge from B to A, then they would still be adjacent. Just there is an edge connecting both of them. Incident is slightly different. Instead of just incident, now we have either incident from or incident to that we have to say. So let's say we've got a situation like, make another page here. Okay, there we go. Okay, so let's say we've got V and W over here. There's an edge from V to W called E. So we say that E is incident from V. E starts at V, so it's incident from V. And then E is incident to W, so it goes to W. We can also say that, let's see, V is incident to E because there is an edge going from V. And then W is incident from E. So we have from and to indicate the direction now. Questions on that? Okay. So for isomorphic, the same idea applies. But in addition to, so one of the things that I want to mention that I saw on the exam is isomorphic. We saw those examples where like if we have K33 and we relabel them, then we would say that it's not isomorphic. But the definition of isomorphic is not only if they're moved around in space, but also they're isomorphic if we can relabel them so that one is equal to another. So you may see that I took a few points off the exam and the homework for that. So two graphs are isomorphic if you can orient them in space, and also if you can relabel one to get the other. And so isomorphic for directed graphs is also the same. But the edges have to agree, like in number and like incidence, like before, and direction. So the orientation of edges also has to agree. Let's say if we've got, let's just look at an example for that one. So if we have this K3, a triangle, which the edges go around like that. If we've got this, where the edges are going out and down like that, these two are not isomorphic. So they're not isomorphic because the directions don't agree. For subgraphs, it's basically same. The edges just have arrows now. One of the terms that you'll see in the problems and in the textbook is underlying graph. It's the graph, but you just take out the arrows. So for example, let's draw this house graph, and we've got just some edges that are assigned here. So this is a digraph, but the underlying graph is just the house graph, but without directions. For degree, so before we had this notion of how many edges are incident to this vertex, now we've got arrows on them. And so we need to split this into two parts. So we've got the in degree and the out degree, which I feel may be fairly self-explanatory, where the in degree is the number of incoming edges, and the out degree is the number of outgoing edges. So let's say if we've got this vertex, the in degree is 1, 2, 3, and the out degree is 1, 2. So the number of edges going in is 3, the number of edges going out is 2. Questions so far? Okay. We've got something that the book calls the handshaking dilemma for some reason. So if you remember, we talked about how the sum of all degrees is equal to 2 times the number of edges. And we talked about that a fair bit. So what does this mean for when we're looking at in and out degrees? So what ends up being true is that the sum of the out degrees is equal to the sum of the in degrees, which is equal to the number of edges. And I hope you can see how that follows. Like, let's look at this very simple graph. So the number of edges, just in general, is 2. The number of in edges is 2, because this vertex got, no, don't erase it. This vertex has 1 in edge. This vertex has 1. The number of out edges is also 2, because this vertex has 1 edge going out from it, and the other one also has 1 going out from it. So the sum of the out degrees is the sum of the in degrees is the number of edges. So it's kind of similar where if you were to add these together, which is the same kind of reasoning that we had with the handshaking lemma, then you get 2 times the number of edges. So if we were to add them, we would get 2 times number of edges. Yeah.
Small thing, I think it's called handshaking dilemma. It's the play on words. This only applies to diagrams.
I love that. Oh my gosh. That's awesome. I love this textbook so much. Thank you for pointing that out. I would have wondered. Okay, any questions? Yeah.
Have you considered both the edges are outgoing to one person?
The number of edges is 2. The number of incoming edges for this one, 0. For this one, 2. Number of outgoing edges for this one, 0. For this one, 2. Does that answer your question? Any other questions? Okay. I will note for like path, walk, and trail, and also like cycles. The idea is basically the same. It's just if we have, let's say we have U going to V, we can take the edge UV, but we cannot take the edge VU, right? We can't go against this arrow. It's like on a one-way street. Like you can't, well, you could if you really wanted to, but it's not a good idea to go opposite the direction in a one-way street. Okay, and so that applies, like for a cycle to exist, let's look at so let's say we've got that's a cycle, right? Because we can start from one, go all the way around to the other. But if we had that instead, that's not a cycle. Because we could start from here and go around, but we can't finish the job and go back to where we started. Okay. So for connected, so the graph is, we say it's connected if the underlying graph is connected. So if we removed all the arrows and the graph is connected, great, it's still connected. If the underlying graph is not connected, then we would say it's disconnected. We do need to, because the part of connected is that there is a path between every pair of vertices in an undirected graph. So we need to add something like that for digraphs. So we say that it's strongly connected, and then we just bring that old definition back. So if there is a path between any pair of vertices, then we say this digraph is strongly connected. Let's look at an example for that one. Five. Okay, so this is a disconnected graph. Like if we treated this as a whole, then it's disconnected. If we look at something like this, okay, let me just draw the one that they have from the book. I was going to try and make it simpler, but maybe that's not going to give me what I want. Okay, so we've got a direction here, a direction here, here. This one goes across. Wait. I might have written it down wrong. I did write it down wrong. Okay, so this graph as is connected. Because if we look at the underlying graph, it's connected. But it's not strongly connected. Meaning that, like, if we look at X and Y over here, look at the bridge, there's no path from Y to X. So it's not strongly connected. If we added, let's say this one goes this way. Oops, sorry, I forgot to silence my phone. And that edge goes no, this way. If we add the orange edges, then we're strongly connected. So yeah, so like if we look at a city with one-way streets, it has to be strongly connected, right? Because we have to be able to get from one part of town to another. There can't be one part that's just cut off. of you can only leave your neighborhood, but you can't get back in. So that's why strongly connected matters. Eulerian, Hamiltonian, those things are also the same, yeah. Okay.
Graph with just allegedly.
Mm-hmm. I think so, because removal would violate the, if you remove it, then the property is violated. Yeah. Other questions? Okay. Yeah, Eulerian, Hamiltonian, it's the same thing, just like with the paths and cycles and stuff. You have to be careful of which edges you can take. So it maybe just adds a little bit to that. And then the last thing we'll talk about, then I'll let you go. That's not the number. Is theorem 4.2, which says a connected digraph is Eulerian if and only if for each vertex, the out degree is equal to the in degree. So that's so we talked about how for an Eulerian graph, the degree of the vertex has to be even. And so this is the variation of that. So the out degree has to be equal to the in degree. Okay, questions before I release you into the wild of solving problems? Okay, so work up to maybe problem 14. I've got markers I'll pass around, put your answers up on the board so that I know that you've done them. I will stop recording and split you into groups to work together. And whoever does the most problems correctly by the end of the class. So we've got maybe, we go to 11:20, like 30 minutes. So the team who gets the most problems done correctly wins chocolate if you want, or eternal glory if you don't.